All right. So resistance, pressure, flow, blah, blah, blah. Change in pressure is equal to the flow rate times resistance, similar to V equals IR. Potential equals current times resistance. So the important things here have already been highlighted and circled. Resistance, it has to do with the size or with the radius, diameter, whatever, of the vessel it's flowing through. And it's not just, it has a little bit to do with it, it has a whole bunch to do with it. Look at this. This is a quartic function, and it's on the denominator. So this means that the smaller the denominator, that's being raised to the fourth, the greater the overall resistance is going to be. Kind of like if you make a fraction, or the denominator of a fraction is smaller and smaller and smaller, the overall fraction is going to, its value is going to increase. You know, like 1 divided by 1 is just 1, but 1 divided by 0.25 is 4. Well, this is a similar thing. The smaller the radius, the greater the resistance. And not just a little bit, a whole heck of a lot, because this is a quartic function. All right. Very incredibly high yield. Arterials account for most of the TPR. Capillaries have the highest cross-sectional area, the lowest flow velocity. This has to do also with the way that things are arranged. A lot of capillaries are arranged in parallel, and as a result, here's how you calculate the total resistance. 1 over total resistance equals 1 over one of them plus 1 over, okay. And in series, you just add them up sequentially. Viscosity, multiple myeloma, increased viscosity, anemia, decreased viscosity. You already know that, and that things flow from high to low pressure with blood, just like with everything else in the world. Here's the big thing, all right? Looking at these curves right here, cardiac output, venous return curves at right atrial pressure. So what's the best way to explain this? Let's start with number or letter A, with inotropy. Let's start with contractility, A, and then see how kind of these graphs work, and then it'll be easier to apply it to B and C. So looking at A, here you have a normal point. Ideally in the world, right, cardiac output is going to equal venous return. It just makes sense, okay? What your heart pumps out, the output, it gets back, the return, all right? It makes no sense if you start pumping out a whole bunch of blood that can't get returned, because then you'd be pumping out blood that you don't have, because everything's a closed system, right? So the idea here isn't that the inotropy is going to increase, but nothing's going to happen to the venous return. No, at first, if your heart all of a sudden starts pumping super strong, it's going to take a second. It's going to take a little bit for your venous system to compensate. However, it will with time. So let's kind of see what's going on here. So let's say all of a sudden you've been pumped full of catecholamines, okay? So what happens? Well, your inotropy goes way up. Okay, so you'd think it'd be right here. However, it's not. Your normal, you can look from your arrows, where cardiac output equals venous return. It's not up here, all right? Why is that? Well, because although you have an increase in your cardiac output here, your venous return hasn't changed. And, like I said in the beginning, and kind of like how you can deduce or induce or whatever, deduce, yeah. Kind of like how you can, think about it. You can't just pump out a whole bunch of blood in a closed system that you're not getting back. Or else you'd just be pumping out air or whatever. So what happens? Well, as your inotropy increases, right here, well, your cardiac output's going to increase. And so your venous return is also going to increase a little bit. And here's what happens. Your new normal point is actually right here. All right. Well, what would have happened if all of a sudden you had a decrease in your cardiac output? Let's say you had a decrease in your contractility, and they'll tell you right here. They say, oh, he's got heart failure or something, or he's been taking narcotics or whatever, right? Well, similarly here, you have a decrease in your cardiac output. But you'll notice how this isn't your new normal point right here. Similarly, how your new normal point with an increase in contractility wasn't just, you just add a few values to, the y coordinate. You also end up having a change in your venous return. Why is that? Well, if you're not pumping out as much blood, you can't start receiving the same amount of blood you were receiving before. All right, that also has to change. All right, and look at this. Look how nice this is. And here we go. You're also going to have a decrease in your venous return. So you can kind of see how things work in tandem, right? And so the same thing applies to graphs B, graph C. Okay, graph B is just talking about venous return. All right, it's saying, hey, look at the tone, look at the volume that you have. So let's imagine a scenario, right, where you have all of a sudden a whole bunch of fluids getting pumped into you. Okay, let's do that right here. Well, look at this. We have an increase of our volume. We have an increase in venous tone. So where's that a normal point? Is it right here? Well, no. Why is that? Well, you can't just have a whole bunch of blood coming back to the heart without the heart pumping out that excess blood. You know, it would leak out of the heart. You know, your heart would explode or something, and that's not good for anyone. So, you know, what happens? Well, you look at this curve. You know, you have an increase in your contractility when something like that happens. Okay, you can kind of do something like that. Similarly, what happens when you have a decrease in your venous tone? Well, let's say you just got stabbed in your aorta and it's just leaking out. Well, okay, well, we have a decrease in our venous return, or we have a decrease in our volume. We have, you know, however you want to phrase it, whatever. And similarly here, it's not like this is your new normal point. So like, oh, okay, honey, I'll just keep pumping out the same amount of blood. Doesn't work like that. Okay, if you're leaking out a whole bunch of blood, you can't just pump out the same amount. Venous return has decreased. You can't pump out the same amount. Why? Well, because what's returning back to the heart is decreased. So the heart's going to have to pump out less. Well, how's it going to do that? Well, you decrease the cardiac output, either by contractility, either by stroke volume, either by whatever. You know, you've got a whole bunch of different ways of doing that. So your contractility is also going to decrease. Look at that. Look at that. Boom. And here we go. Things working with each other. So what happens when both are affected? What happens with something like total peripheral resistance? Well, I can tell you right now, increase in total peripheral resistance. Well, we talked about how the afterload is going to mess up something like cardiac output. You can kind of approximate or think about you know, the afterload in terms of the work the heart goes against, which is related to the mean arterial pressure. Okay, well, so when you have an increase in this total peripheral resistance, the contractility, not the contractility, but the output's going to be decreased. You know, eventually through contractility and stuff, but that's not what I was trying to say. Here you have an increase in total peripheral resistance. Your heart's not going to be able to pump out as much. In addition, also, increase in total peripheral resistance, it messes up, you know, the blood return also. However, when you have a decrease in your total peripheral resistance, you can think of it kind of as a decrease in your afterload or whatever. All of a sudden, the heart can pump, you know, without any problems, without any restrictions. You know, all systems go, green light. And similarly, when the heart can pump out all that stuff, you know, you're not going to have any sort of problem with returning everything back. Because remember that for things to get back to the right atrium, the pressure in the right atrium should be damn near zero. It should be very low. If the pressure in the right atrium is very high, and you remember how things flow from high to low pressure, well, then if things in the right atrium are super high, well, then the blood would theoretically flow backwards and not into the heart, which is absolutely not what you would want. And so here we go. And different points on different things, you can see how everything kind of reaches a nice equilibrium here. So that wasn't too bad. Okay, we went through V equals IR, you know, flow, resistance, how the size of the vessel influences the resistance, where the most resistance occurs, arterioles, okay, capillaries, things in series, things in parallel, and then these way cool cardiac output venous return curves. All right, understanding that the new normal points, you know, they shift because you need to have cardiac output eventually equal venous return. You know, maybe not the first little bit, but you know, eventually it's got to happen when you're going to run into problems.